Hello, and welcome to Week 6 of Quantum Mechanics for Liberal Arts. In this week, we'll learn about one of the most fascinating and mysterious aspects of quantum physics, entanglement. Entanglement is a phenomenon in which two or more quantum particles, such as electrons or photons, become so strongly correlated that their quantum states are linked together, even when they're separated by large distances. This means that measuring or manipulating one particle will instantly affect the other particle, no matter how far apart they are. This sounds very strange and counterintuitive because it seems to violate the principle of locality, which says that physical events can only be influenced by their immediate surroundings. How can two particles communicate faster than the speed of light? How can they know what the other particle is doing without any physical connection? These questions have puzzled physicists and philosophers for decades. To understand how entanglement works, let's look at an example. Suppose we have a device that produces pairs of photons with opposite polarizations. Polarization is a property of light that describes the direction of its electric field. For example, if the electric field oscillates vertically, we say the photon is vertically polarized. If it oscillates horizontally, we say it is horizontally polarized. Now, suppose we send each photon in a pair to a different location, say Alice and Bob. Alice and Bob each have a device that can measure the polarization of their photon along any direction they choose. For example, they can measure whether their photon is vertically or horizontally polarized, V or H, or whether it is diagonally polarized at 45 degrees, D, or minus 45 degrees, A. According to quantum mechanics, before Alice and Bob measure their photons, each photon does not have a definite polarization. Instead, it exists in a superposition of all possible polarizations. This means that each photon has some probability of being V or H or D or A when measured. However, once Alice measures her photon along some direction, say V or H, she will get a definite result, say V. At that instant, her photon collapses into the state V and loses its superposition. But what happens to Bob's photon? According to entanglement theory, Bob's photon will also collapse into the opposite state, H, at the same time as Alice's measurement. This means that Bob will always get H if he measures his photon along V or H direction. The remarkable thing about this correlation is that it does not depend on how far apart Alice and Bob are from one another. They could be in different rooms, different cities, or even different planets. As long as they share an entangled pair of photons, they will always find perfect correlations between their measurements. This implies that there is some kind of non-local connection between their photons that transcends space and time. But how does this connection work? How do the photons know what state to collapse into? How do they communicate faster than light? These are some of the questions that entanglement raises and challenges our common sense notions of reality.